All right, welcome back. So we are on the final unit, and this is going to be a whole slew of things involving sequences and series, and there's a whole lot of tests and rules that kind of go along with this. So we'll start slowly tonight, and we'll start to build. Um, so we are going to be defining convergent and divergent infinite series. And to get into that, the first thing we're going to look at is a sequence. And a sequence is a list of numbers with a pattern. So we're going to start real basic, and then we build and get a little crazier as we go. A sequence is a list of numbers with a pattern. This is called an arithmetic sequence, and that just means that your pattern is going to be consistently adding something each time. So 1 to 4, 4 to 7, pretty clear. That's plus 3, plus 3, plus 3. That is called an arithmetic sequence. And there's two major ways to express this, and that's called recursive and explicit. So in a recursive formula, you have something that is like very easy to say. If I want to find this specific term, here's my formula that does that. Um, Explicit is going to be basically you list out these terms, and it's going to be in the format order of the term, comma, actual value. So like this is the first term, second term, third term, fourth term, and then the actual value is the y value of that piece. And what you do with it is you find the slope. So that means you could pick any two of these ordered pairs and find the slope. And then you use point slope form, and we can write a formula out that shows you what a sub n would be equal to. This is pronounced a subscript, so we call it a sub n. You'll hear us saying that a lot. Uh, so if you want to take a second and copy that down, we're going to have you try one on your own here in a second. Okay, so on our own, we want to come up with a recursive and an explicit formula for what we see here. So we've got 1, 5, 9, 13, and we are going to come up with, so for recursive, basically, you're just coming up with a sub 1 is equal to, and we already know that that's 1. And then for a sub 2, it's going to be, what's our pattern? It's going to be a sub 1 plus 4. So then a sub 3 is going to be equal to a sub 2 plus 4. And then we can make the generalization a sub n is equal to, now this is an important term. This stands for the term before it, right? A sub n minus 1 is the term before it, and then plus 4. Okay. So now the key here when you're doing recursive, you've got to know the term before it in order to come up with an answer. Whereas with explicit, you can go right to an answer and you don't have to have that previous information. So what do we have over here? We have the point first term, actual value. Second term, actual value. Third term, actual value. Fourth term, actual value. If we go through there, we can locate the slope of this, and the slope of this would be whatever ordered pairs you want to use, but the slope of that should be 4. So I'll just use these first two ordered pairs. And then when you go through, now it's going to be a sub n and then minus, so I'll use specifically this first ordered pair. So y minus y1 is equal to the slope times x minus x1, except instead of x and y, your ordered pair is n comma a sub n, the number of the term comma, and then the actual value. And then if you solve that out, a sub n is equal to 4n, and then that's what, minus 4 plus 1. So the explicit formula is, oops, should have been a minus sign, sorry. 4n minus 3. Okay. All right, so this is just some practice using these formulas. Using the explicit formula an, and it's going from 1 to infinity. N equals 1 to infinity. Write the first 4 terms of each sequence. The first 4 terms of each sequence. So you're just going to go through and plug in 1, 2, 3, and 4 into both of these. Okay, so go through and try to find all 8 of these, and we'll talk in a minute. Okay, here comes some answers here. Tell me if you have any questions on these. So here's what I got when I did this earlier.
How did you get 2/5? By one.
Okay, let's see. So if we plug in 2, that's -1 squared plus 2 over. Then maybe is that a typo? Let's see. Over 5. -1. It looks like 3/5.
How are you adding +2 though?
Or no, times 2. Why am I putting a plus sign there? I just answered my own question. It should be. What's
Well,
that?
it's just -1 squared, right?
Yeah, so that's 1 times 2. So it should be positive 2/5. Yeah. Where anywhere you see an n,
Oh, I thought that was -1 to the power of n.
It is.
Oh,
But if you put in a 2, -1 squared is going to be +1.
oh no, I thought the n was a caret, not a.
Oh, I got you. Yeah, so sorry, that's n, and that's an n.
Okay. Okay.
Okay. Next up, we've got the same deal, but we're going to look at a geometric sequence. And a geometric sequence is going to be the same thing as arithmetic, but you're multiplying by the same thing each time. Instead of arithmetic, you're going to be adding the same thing each time. So in this sequence down here, this looks to be times 2 times 2 times 2 times 2. So that's how we're going to start to identify a geometric sequence. And the formula for a geometric sequence is a sub n is equal to the first term times the ratio raised to n minus 1. So there's, unfortunately, guys, there's a lot of formulas coming up in this last unit. So try to keep track of them, write them down. We're gonna have to do some studying. So for geometric sequence, a sub n is equal to first term times the ratio raised to n minus 1. Okay, next we have what is called the limit of a sequence. And when we go to evaluate this, there's two main choices here. And you're going to hear these two words a lot this last unit. The limit as n goes to infinity, a sub n, if that limit is equal to L, whatever L is just a placeholder. That means whatever the limit is. If the limit exists, the sequence converges to whatever the limit is. If the limit does not exist, then it's called diverging. So diverging would be like it takes off. There's no direct answer. Whereas if it converges to something, then you're getting a specific answer. So this is the limit as n goes to infinity is equal to L. If the limit exists, then the sequence converges to L. If the limit does not exist, then it is called diverging. This is an important thing to have written down. Okay, find the first four terms and then make a conjecture on where the sequence goes, converges or diverges. So if you're going to find the first four terms, you're looking for A1, A sub 2, A sub 3, A sub 4, and seeing what we can come up with. So see what your results are. We'll talk in a minute or two. Ready? Go. Okay, so if we put a 1 into this, that should be negative half. For a sub 2, we should get 1/5. For a sub 3, we should have negative 1/10. For a4, we've got 1/17. Does anybody have any questions or objections to those four? Okay. All right. So if we look at this now, we're going to say for a conjecture, we're going to say the limit as n goes to infinity for the thing we just looked at, n squared plus 1. And when we evaluate this limit, well, what's going to happen as n goes to infinity? Think about what happens there. Every time it changes, it's either going to be positive or negative 1, right? So if it's a positive number, it's positive. If it's a negative power, though, then you can keep that as a negative number. So we can say that that's plus or minus 1 over. But now what's happening on the bottom? That's going to be infinity. And regardless of which version of the number 1 you have, that's going to be equal to 0. And so since we have a definite limit, your result is converges. Okay. Any questions there, guys? Okay, let's try again. Same directions. A sub n is equal to cosine n pi. And we're going to go through, find the first four terms. Find the first four terms, and then we want to come up with a conclusion. Okay, so I'm looking at the first one being if you put just a 1 in, cosine of pi is negative 1, then it would go to 1, then it would go to negative 1, then it would go back to 1. So now in this case, when you evaluate this, the limit as n goes to infinity for cosine n pi, we can't come up with a definitive answer here, right? Because this is just going to keep, it's going to be alternating between negative 1 and 1. Therefore, we would say the limit does not exist. Therefore, it is something that diverges. Okay. All right, let's keep going on that train and let's try the next one. Same drill. So let's find the first four terms just to help you kind of practice. And also then come up with a conclusion. Okay, go. All right, so we've got some results there. And as we set up the limit as n heads to infinity for 4n to the third over n to the third plus 1. So you got to think about what this means. As you go to infinity, these two terms are going to be the same thing. And as you get to infinity, when the numbers are that big, we're talking 10 trillion or whatever, 10 trillion plus 1 versus 10 trillion, those are the same number. So you can kind of just ignore that piece there. And these are essentially going to just wipe out. And then that means that your limit is just going to be equal to 4. Because as you plug in gigantic numbers, the plus 1 isn't going to change your answer any. So then therefore this would be something that converges. Okay. So this unit is, it takes a little while to wrap your head around what's going on because it's definitely way different than the calculus we're used to looking at. Do you guys have any questions up to that point? All right, we will do one more question here for tonight and then we'll call it because we're going to be doing these kind of problems here for a couple of weeks. I've got a whole bunch of stuff we got to cover. So let's read here and see what we got. A basketball is tossed in the air and it reaches a high point before falling to the floor. With each bounce, the ball rebounds to 0.6 of its previous height. Let h of n equal the high point after the nth bounce with initial height of 20 feet. So when you see initial height of 20 feet, that's like another way of saying h sub 1 is equal to 20 because each one of these is going to be the next bounce, the nth bounce. Okay, we want to write recursive and explicit formulas. So see what you guys come up with. We want to write a recursive and an explicit formula. So as you're thinking through that, let me ask you this question. Is this arithmetic or geometric? So each one of these bounces is 0.6 of the prior. So what kind of math would you be doing there to go from one to the next, right? So think about what we had said earlier. Find it for you right here. Geometric sequence. Your formula for a geometric sequence is a sub 1 times the ratio raised to the n minus 1 power. So when we're coming into that, hopefully it would make sense to say then that h of n is equal to 20 times 0.6 raised to the n minus 1. If you go the other way, what do we know? H of 1 is equal to 20. And then as we go through here, what would we do? So like h of 2 would be equal to h of 1 times 0.6. And then so on and so on. So as you keep going, you would just, whichever one you wanted, it would just essentially just be the previous term times 0.6. Because your picture of basketball bouncing, it's going to keep going lower and lower and lower. Do we have any questions on that one? Okay, height after the 10th bounce. So I believe you could use a calculator for this question. So h of 10 is equal to 20, 0.6 to the 9th power. How did I get 9? We're plugging in 10 for n, and then 10 minus 1 is giving you 9. And if you toss that into a calculator, that would be 0.2015 approximately. And for our last one, if we want to do a conjecture on converging and diverging, we want to set up the limit as n heads to infinity for 20 times 0.6 to the n minus 1. Okay, I will give you guys a second to think that through. Maybe it might help you to convert this 0.6 to a fraction. I don't know. If you converted it to a fraction, that's 3/5. that might help your thought process a little bit. But anyways, I'll stay quiet for a second, see what you come up with. All right, so this would be the same thing as saying 23/5 to the n minus 1. So as we do that limit value, we've got a picture of what's happening here. So if this is 23/5, and if you raise this, I'm just going to put infinity up there because it's just going to keep getting bigger and bigger and bigger. In other words, you got to raise both sides of this fraction to 0. Well, as you keep raising the powers on this fraction, what happens? Are they getting bigger or are they getting smaller? This fraction would be getting very, very small, so small that it's approaching 0. So then our answer is 0, and therefore you can say that it converges. Okay. Any questions out there? All right, that will conclude part 1 on sequence and series. So we'll pick up there on Thursday night. So have a good week, guys, and I will see you Thursday at 8:30.